The idea of this presentation is to talk about how we can improve the performance of Java without necessarily having to change any of the things that you do in terms of your code. Well, sort of, hence the sort of part of the title. I've got to say that the title of this, I'm still kind of trying to work on whether I can come up with a better description of this. But essentially what this is about looking at how some of the way that other languages, specifically C and C++, use memory layout to get an advantage in terms of speed, and then being able to map that into Java so that we can get the same advantages in Java, something that we can't do at the moment. And it's really about the idea of structs. So if I can actually see anybody. Right, so who here has programmed in C or C++? Okay, good, everybody. So I don't have to worry too much about understanding the concept of structs, but we'll explain a bit of how they work underneath as we go through. Now, the object of this project, which is called Object Layout, is all about trying to match the speed benefits that C, like languages, get from the way they lay things out in memory. So this idea of using structs lays out things in memory in a specific way, so what can we do in order to take advantage of that? And doing it in such a way that it doesn't require complex changes to our code. You might have to do a little bit, but it's really more about using like a different collection. So that's the kind of changes in code that you're going to have to do, using a different collection rather than, you know, a list or an array list or something. There are three key points here. It's about speed for regular Java objects on the heap. And we're going to say that a few times as we go through. So speed, regular Java objects on the heap. What this project is not looking at is a number of things. So one is it's not trying to reduce the footprint of your application. So even though we're experimenting with memory layout, we're not looking at making things smaller to improve footprint. We are not looking at off-heap solutions. So, as the words say, speed for regular Java objects on the heap. And we're not looking at immutability. We want you to be able to use Java objects in exactly the same way that you do at the moment. So if you decide that your Java object should be immutable, fine, it can be immutable. If you decide that your Java object should be mutable, then you can use it in exactly the same way with the Object Layout project. If you look around, there are a number of projects going on at the moment being suggested for inclusion into Java that may appear to be similar. You may think to yourself, well, how do these things relate to object layout? And there are some things where there's overlap in terms of the functionality, but in terms of the goals that object layout has, and if you look at some of these other projects, value types, for example. Value types is a proposition for something that will be included in JDK 10. And it's more about allowing you to do things like treating something as an object, even though it's not really an object. What I mean by that is you can have, right now, if you want to have a list of integers, then you have to have a list of integer objects. You can't have a list of primitive ints. What value types is designed to do is to allow you to do that kind of thing, to have a list of primitive ints. It's also more focused on the idea of having multiple values being returned from a method without having to encapsulate them as an object. So returning a tuple rather than an object. So in terms of the goals of value types, there's no overlap with what we're trying to do with object layout. Another thing that people are looking at is packed objects. And this is much more about the sort of foreign function interface and a replacement for JNI, Java Native Interface, so that people can link code from native compiled code into Java applications and make it accessible. So again, there's no overlap in terms of the goals of that project with object layout. Object layout is focused on this problem of regular Java objects, speed on the heap. There is a little bit of overlap in terms of the functionality. But it's the kind of overlap that, as the example says here, that you can say, well, an array list is a way of collecting together objects. A hash map is a way of collecting together objects. So there's overlap in that sense, but there isn't a lot of overlap in terms of the way those things work. They are both containers for groups of objects, but how they store them is very different. If we use a Venn diagram to represent how these three disparate projects work and the qualities that they have, there is some overlap in terms of the things they do. If we look at value types, really the properties of these things are, one, they are immutable. They are values, so they are immutable. They are focused on the idea of being used for return values, for generic types, so that you can use them rather than an object. And they can be used either on the heap or on the stack, because if you're returning something, you will return it from the stack. In order to use value types, you will have to write new code. You will need to code things differently to take advantage of value types. Packed objects. These are primarily focused on data which is stored off the heap, data which is coming from a piece of native code, so it may be stored anywhere in memory. It's very much about sharing data between native code and Java code. And the other thing is that with packed objects, you're very much talking about precise layout control. The sort of example that you could use there is that maybe you've got some native code which is bringing in TCP packets. Those TCP packets have a very well-defined structure which needs to be maintained in order for them to be processed within either the native code or the Java code. So you've got to have control of the layout of the data. Again, for using packed objects, you will need new code. You will need to rewrite things in order to take advantage of those. With object layout, we are talking about speed for regular Java objects on the heap. And if you look at the Venn diagram, there is this little bit in the middle where all three of them overlap. And so, yeah, objects usable by all existing code. So the idea is here that we don't want to change any code drastically in order to take advantage of object layout. The overlap is essentially if you had an array of small footprint values. So there are a few situations where you might find that you could use all three of these together. Now, the origin of this project was really when Gil Tenney, who's the CTO of Azul, was having a discussion with Martin Thompson and talking about how to improve the performance of Java. And the kind of argument they came up with is, well, we need structs in Java. People have tried to replicate structs in Java to take advantage of the speed that you can get from them. And they do that in numerous ways. They use things like sun.misc.unsafe in order to be able to get down to the low-level manipulation of the memory that's being used by the JVM. And as we know, in JDK 9, sun.misc.unsafe is going to be deprecated. It's due for encapsulation at some point in the future. So it's really not a good idea to be using private interfaces to do this kind of thing when they may either disappear or have to be modified to make your code work in the future. If you look at C and C++, because they have structs, they get this thing for free. So the other side of the argument when it comes to Java is, well, we already have structs, because if you think about a struct is just a way of grouping together a number of pieces of data. In Java, we do that with objects. So we create a class, we define which pieces of data we want to go in there, and that gives us our encapsulation of the data. So we call them objects, C and C++ calls them structs. What we need is a way of using objects and making them as fast as structs are in C and C++. And the important thing is figuring out how to do that in a way that will make it simple enough for people in the Java land to use them. How do we do that? Now, the first thing we need to kind of look at is, where does this speed come from? So I'm telling you that structs are faster and more efficient than objects. Why is that? Well, really it comes down to two things. The first is that if you want to access a particular piece of data within a struct, you can do it through dead reckoning. Now, I'm going to explain what that is in a moment in terms of how it works. The other thing that you can do is if you have an array of structs, you can stream over it and use the stride of it to give you an advantage in terms of how you access that data. Let's look at that in a little bit more detail. So pretty much everybody here has already used C, and so they know about structs. If I want to define a struct, I do something like this. I create a struct called a square. It's going to have 3 pieces of information in it, 3 ints, x, y, and size. And then I can create one which will put it onto the stack. And if I look at what's being stored there, the diagram represents what I'm going to have. I'm going to have 3 integers pushed onto the stack and represented as my struct. What I could then do is I could say, okay, let me create an array of structs in order to use them. And because C, we'll use C as our language, because C doesn't have the concept of a new operator, we need to explicitly allocate memory for the number of structs that we want to store. So in this case, I'm going to allocate enough memory to store 5 structs of square. And so I get my 5 structs in an area of memory which is contiguous. So each of the structs is next to each other, and that's all good. The great thing about this is the fact they're contiguous in memory. If I want to find the address of a particular piece of data in my array of structs, I can do it like this. So I can say, I want to find the y value associated with the 4th element in the array. And of course, because we're computer scientists, we start counting from 0, unlike humans who start counting from 1. So we're actually using index 3 rather than index 4. Of course, unless you're Pascal programmers, I suppose. So how do we do that? Well, we can start by using the address of the beginning of our array of structs. So this is the reference that we got when we allocated the memory. We know that we want to move by 3 sizes of the struct to get to the 4th one. So we can simply add 3 times the size of the struct to that address, and now we know we're at the beginning of the 4th element. If we then add the size of an int, we're moving past the first integer in that struct to the second one, which is the y value. Great thing about this is this only requires a calculation. There's no having to go through a pointer in order to find the data that we want. So there's no having to retrieve the pointer, then use that pointer to reference the memory. There's no levels of indirection. It's simply a calculation, and that can be very quick. The other thing is, if we want to iterate over our array of structs, and that's something, as we know, we do a lot with data. We want to iterate over it to maybe search or find, sort, or whatever. And because we know the size of the struct, it becomes very simple. We start off with the address of the area of memory we've allocated, and then to get to the next one, we simply move on by the size of one structure, then we move on by the size of another structure, 3 structures, and 4 structures. And so again, this is very quick because it's calculated. But the other thing is that the underlying hardware can take advantage of things like prefetching. So the underlying hardware will spot that we're accessing a sequence of memory addresses and will start loading the data for us in advance to give us better performance. We can also get better cache coherency, we can get better use of the cache lines in order to make this work in a better way. So that's all good. That's how things work in C. Now let's look at how things work in Java. So rather than creating a struct, what we're going to do is create an object or a class. Then we'll create instances of that class as an object. So we create our class, and it looks very similar to the struct. So we simply have 3 values, x, y, and size. They're ints. And if we look at the square object, we'll find that, yes, those three things are probably stored contiguously in the object. But there will actually be extra stuff around there. You'll have an object header, you'll have some other things, especially if there's code associated with it. And we can create one of those simply by instantiating it using the new operator. So that's kind of similar. What happens if we create an array? Well, then things look very different because now the heap is involved and we have to use the virtual machine to handle memory allocation for us. So what we end up with is a situation like this. We create an array of squares and we want 5 squares, and then assume that I create 5 objects to add to those. If we're very lucky, we'll get 5 of these objects allocated sequentially. Now, that could quite often happen depending on how your memory allocation works in terms of the heap. So if you're using the young generation and you're using a single thread, yeah, you might be able to get it. If things like thread local allocation blocks kick in and you move off to another block, then these things won't necessarily be contiguous in memory. But let's assume, for the sake of argument, that to start with, they are contiguous in memory. So we could, in theory, still use our striding, we could use our way of calculating the address of a particular piece of data. However, problem is that garbage collection comes along and the objects get copied from the young generation either to the survivor spaces or into the old generation. And then things aren't guaranteed to be kept contiguous. Now, a couple of people have kind of said to me, well, if you're using a copying collector, yeah, you probably will get contiguous data. And it's like, well, okay, you might get contiguous data. But the point is, you can't guarantee that because there are certain situations, definitely, where garbage collection will move things around and you won't have your data contiguous. But of course, the problems are actually more complex than that because we could very easily, even if we had our data contiguous in memory, we could come along and we could say, okay, I'm going to change the element at the end of that array. I'm going to create a new square for some reason, and I'm going to associate that with the last element of the array. So that's now going to be somewhere else in the heap. And things get even more complex than that because we're using an object-oriented language. Therefore, we have inheritance. So I could come along and I could say, well, I've got a new class called filled square, which has extra stuff in it, and I want to store one of those in my square array. So I say square 2 is now going to have a filled square in it. Filled square doesn't have to be the same size as square. So again, there's absolutely no guarantee of contiguous data because of these various things. So when we look at the semantics of structs versus objects, in C, a struct array is an immutable array of exact same size structures. We saw that when we created it because you have to create the array of those structures, so they have to be of that structure. There's no inheritance in C, so you can't have a substructure in effect. And so they have to be the same size. And you can't change what's there. You can change the values in the struct, but you can't change the actual struct itself. In Java, we have a different case. We have an immutable array, of same base type objects. So we can change the references that are used from that array. So we can change the references from the array to the objects. So that can change, as we saw in the diagram. And we can change the type of those objects. Anything that's a subclass of, in our example, square, can be stored in a square array. So these things are what limit us in terms of getting performance out of this. Now, the object layout project is designed to address 3 specific situations in terms of common usage. The first of these is having an array of structs. So how can we replicate that in our Java style? The second one is having a struct which also contains another struct. And then the third one is having a struct which has some values and then an array at the end. So that's very typical if you're using something like a packet. Now, we can represent all of these in Java. No problem at all. We can map them in terms of creating classes. We can create objects that will do that. But the thing we can't do is match the speed of C and C++. The idea behind how to make this project work is based very much on what happened with java.util.concurrent. So before Java SE5, if you wanted to write multi-threaded code, it was really quite difficult. In order to coordinate the actions of multiple threads, you essentially had only 4 primitives from the thread class that you could use: wait, sleep, interrupt, notify. In Java SE5, well, before Java SE5, there was a project that was started by Doug Lee. And he looked at this and he said, well, it'd be really good if we had some higher level primitives that we could use for multi-threaded code. So he went away and he wrote a set of classes. These classes included things like semaphores, mutexes, atomic operations, and all those good things. And the way he did that was to just use pure Java. So there was no requirement in terms of changing the JVM. There was no requirement in terms of changing the language itself. So he was able to write these classes just using normal Java. When you run those things on a normal Java virtual machine, which doesn't know anything about them, then you implement them in maybe not the most efficient way. So for example, with something like an atomic long compare and set. You can do that by doing synchronized bits of code underneath, but it's not necessarily going to be the most efficient way of doing it. Once in JDK 5, these classes got moved into the standard class libraries, then the JVM was able to go, or the JVM developers were able to go, we know about these things now, so we can actually improve performance by intrinsifying the way the code works for that particular case. If we look at atomic long compare and set, we can move away from having several synchronized blocks of code involved to using a single x86 instruction. So suddenly it becomes a lot more efficient. And that's the idea for the object layout project, is we'll start off by writing a set of Java classes which simply use normal Java to do the work. Then, as the JVM becomes aware of these things, it can intrinsify how that code works and then give us an advantage in terms of performance. So we'll talk more about how that works as we go through. So the starting point for the object layout was really to look at the semantics of how things worked for giving us the speed of structs. So we needed to figure out how do these layouts work in such a way that we can get this speed, but without changing the language, without changing anything which would break existing code. And in terms of targeting this, we targeted Java SE7. There's a reason for using Java SE7 and not earlier versions, as we'll see a little bit later on. But in theory, we're using Java SE7, but just the standard classes, the standard language features from Java SE7. What we then want to do, obviously, is to say, let's have the JVM, once it recognizes these things, take advantage of its knowledge of these things and can then improve performance. So we can figure out how to intrinsify the code, give it better performance from a memory perspective. Let's look at the first of these then. So how do we deal with an array of structs and mirror that in terms of Java? And the answer is with a new class which is called structured array. It's very much like a collection. So it's a structured array which has a type associated with it. So we can create generic instances. What this is a collection of object instances of an arbitrary exact type T. Now that's really the most significant part, is that description. So they are exact type. That means that you can't have subclasses. So you can only have whatever type T is. No subclasses of T, which eliminates that problem of having a filled square in a position where we've defined it as holding a square. This is very much like a C-struct array. This is arranged, as you would expect, like an array. So if you want to reference an element in the structured array, then you can use an index to say, I want the element at position whatever. And so you do get index. The collection is immutable. You cannot replace elements in this collection. Again, this is so that it adopts the same semantics that are used in an array of structs in C, because you can't change the actual struct. You can change the values inside it, not the actual struct. So in the case of the structured array, you can change the values inside the objects which are stored in the structured array, but you can't change the references from the individual indexes. They stay the same. Therefore, we have a get method in order to retrieve an object at this particular index, but there's no put method because we can't change things. So there's no chance to be able to put an object at a particular place. To create a structured array, we use a factory method. And there's a reason for this, which will become apparent, which is to enable us to simplify the construction of these things. If I want to create just a simple structured array, use the factory method new instance. What you pass to that is the class which you want the structured array to hold. So in this case, I've got some class. I will create an array of objects of some class. And you tell it how many of those objects you want in your array, the size of the array, in this case 100. And that will create an array of 100 elements of some class. The important thing is that all of the elements are constructed at instantiation time. So all these objects are created, they're placed into the structured array, and then they're ready to use. There's no lazy evaluation, there's no constructing them when they're actually required. They're all constructed when you create the structured array. Quite often, in fact very often I would expect, when you create objects and you want to put them into a collection, you may well want to use the constructor to pass in values. You may want to do something special when you construct your objects. To support that, there is a thing called the CTOR and args class, the constructor and args. What that allows you to do is to specify how each object is created from the point of view of the constructor based on its index in the structured array. I'll show you an example of that on the next slide. Let's assume that we have a class called foo. This has a simple structure to it. It has a variable called index, and it has a constructor which takes an index of type long and stores that index. If we want to construct a structured array of these, then what we need to do, in the case of where we want to store the index into each object as it's created, is first to retrieve via reflection a constructor for the class that we're going to create. So we take our foo class, we get the constructor from that, and we say that we want the constructor which takes a parameter of type long, so a primitive long. And that gives us a constructor of type foo. Then when we construct our structured array, we use the method, or the factory method, new instance. We pass in the class as we did before, so foo.class. We also pass in the number of objects that we want created, so 8. But we then have the idea of how we could actually, we pass in what's called a constructor and args provider. And we do this using a lambda expression. So the idea is that by using a lambda expression, we're not actually providing the object, we're providing a description of how to construct the object. So the actual new instance code can use that lambda expression to construct the objects that it's going to put into the structured array. How that works is that the constructor and args provider is passed a context. And the context allows you to get information about which object is being created at a given time. From that, you can get the index. And then when the new instance method wants to construct those objects, what it will actually do is it will call the constructor that's been passed in and pass the index of the object that's being created to the constructor. So when the object's constructed, it has the appropriate index, and you get that stored in the structured array. Now that's quite a simple example. If you want to do more complex things, clearly you can define Lambda expressions that do whatever it is that you want in terms of constructing those objects. Liveness was something that was considered in terms of the structured array. The initial thought with this was that if the structured array had any objects in it that were, if there was a reference to elements in the reference to elements that were in the structured array, then that would keep the structured array alive, even if there was no reference to the structured array. So that was a very different approach to the way things normally work in Java. But if you think about the way things work in C, it's kind of mirroring what happens there. You know, you've got your array of structs, and if you need to keep a reference to one of those, you keep the whole thing alive, because you can't free up the memory that's being used unless you copy the struct out into somewhere else. But of course, that's not really the way things work in Java. So what was then thought was, well, okay, objects already have real liveness in Java. JVM tracks them for the purposes of garbage collection. So rather than doing the situation where if you've got a reference to an element which is in a structured array, you keep the structured array alive, what we'll do is just say the structured array is like a regular collection. Same as if you've got an array list. You've got an array list which contains objects. If you have some references to the objects that are stored in that array list, those objects will be kept alive. But if the reference to the array list disappears, then the array list and any objects within that that aren't referenced can all be garbage collected. So now the same thing applies with structured array. If you stop referencing the structured array can be garbage collected. And anything that's within it can also be garbage collected as long as there's no references to it. The essence of that is it works exactly the same as things in Java already. Now, in terms of the benefits of this liveness approach is that structured array simply becomes just a collection of objects, which is good because then there's no special behavior that's different to any other collection. So we don't have to think of it differently. Even though we're trying to model an array of structs, we can still think of it like a collection of objects. And where the JDK is able to optimize that, you get better performance. So the elements of the structured array are just regular objects, plain old Java objects, nothing different about them. So they can participate in any way that any Java object can participate in any Java code, which means you can put them in other collections. It means you can make them part of object graphs, you can pass them around, anything you want to do. You can lock them. You can use the hash code for identity. Anything you want to do with a Java object, you can do with something that's stored in a structured array. You don't have to treat it any differently just because it's in a structured array. So very natural in terms of how we use them. Features of the structured array. Well, indexes are longs. Great, because we know that it's 2016, so there's no point in using ints because you may well want to have quite large numbers of objects in your structured array. It is possible to nest structured arrays. So if you want to create multi-dimensional, composable structured arrays, you can. So you can have a structured array which contains elements which are themselves structured arrays of some type. Nothing problematic in that at all. Structured array is subclassable. There are a number of situations where we can see that it would make a lot of sense to be able to take structured array and create your own subclass of that collection and use it in particular ways. So that's good. Structured array is not composable. We have to use factory methods in order to deal with a number of the sort of things that have to be done in terms of constructing the objects and so on. So you can't call the constructor directly. You must use a factory method in order to create your structured array. Now, the observant amongst you will spot there's a little bit of a problem with that because in Java, if you want a class to be subclassable, it must have a publicly accessible constructor. But of course, we're just saying that the constructor can't be called directly. So how do we get around the problem of having a constructor that's publicly available and not being able to call it? Because that's kind of counterintuitive. The answer is something called constructor magic, which solves all problems. Essentially what happens is that when the constructor is called, it looks at where it's being called from. If it's being called from within the factory method, then it knows, oh yes, that's fine, so we can use that constructor and we can do whatever's needed. If the constructor is called from outside of a factory method, so if you try to call it directly, the constructor will spot that and it will throw an exception. So you can't, although you can, strictly speaking, you can call the constructor, it won't work. So it solves the problem of not being able to use the constructor while still having a subclassable class. But optimizing for the idea of a structured array. To do this, what we do is we essentially determine that an object is now either contained or a container when it's being used in this situation. A container will be our structured array. It's something that holds references to other things. A contained object is one that's placed inside a structured array. So when we're dealing with a structured array, we have containers and we have contained objects. From the point of view of our code, that makes no difference. We don't see any difference. But from the JDK, what it can then do is say, okay, we know that these objects have specific properties. If it comes across an object that needs to be garbage collected, it looks at it and says, is this a contained object? If it is a contained object, the JDK, the JVM, now knows that it's part of a structured array. What you can also do is it can take a contained object and find the immediately containing object. So it can find the reference to whatever has it contained within it. So we trace back from the object to the structured array, and then we can find any other objects which are contained within that structured array at the same time. That way the garbage collector, rather than having to treat individual objects on their own, can then say, right, let's look at everything that's in that structured array and treat it as if it were a single unit. And then rather than moving individual objects, it moves the whole thing as one. And that solves the problem of contiguous memory. As long as they're contiguous in memory to start with, then they'll be contiguous in memory as we move them around, because the JVM knows about the contained container relationship. This is actually fairly simple to do. We at Azul have the Zing virtual machine, which does garbage collection in a slightly different way, but we've worked on that and we proved that it's quite possible, quite reasonably simple to implement this and get better performance from it. In terms of taking advantage of this and getting the benefits of things, streaming benefits don't require any extra work. They come straight away because you've got everything contiguous in memory. If you start iterating over your array, then the underlying hardware, JVM, can immediately pick up on that and start using prefetching, using better caching and so on to give you the advantage. Dead Reckoning is a little bit more complex and requires a bit more compiler support because a struct is just a way of grouping together pieces of data. An object is more complex than that. You have an object header, you have other things that go around it. So when you want to calculate the position of a particular piece of data within a given object, you have to take into account the object header, you have to take into account the layout of the data within that, and do a little bit more calculation, or not calculation, but a little bit more processing in the compiler to give you that benefit. There's a couple of things that have already been done which you can use a similar kind of approach, things like class hierarchy analysis, inline caching. Those types of things apply very much in this situation. Looking at the other two situations that we're trying to address, the idea of a struct within a struct and a struct that has a variable and then an array of things at the end of it. So let's look at how we would have an encapsulated struct in C. So here I've got a struct called line. within that I've got two point structs, endpoint 1 and endpoint 2. And they have an X and a Y value, which are ints. So very much the same as we saw before. We have everything kind of neatly compressed, and we know that we've got all these integers there. Things obviously look a bit different in Java because whenever you have a reference to an object, it's a reference. It's not the actual object itself. So if we create a class called line and we create 2 point objects, 2 point object references from that, the objects themselves will not be stored in the line object. They will be referenced from the line object but stored elsewhere. So we end up with the kind of situation that we have there. To solve that, what we have to do is we have to tell the compiler, and therefore the JVM, what we're actually trying to do. So we need to make whatever object we want to reference intrinsic to our object. What we do here is we say, okay, in order to do that, we'll create our point endpoint 1, we'll mark it with an intrinsic annotation, and then we'll construct it within this object, or at least we'll call it construct it within, using an intrinsic object. And in order to do that, firstly, we have to pass in a method handle. So this is why we need to rely on Java SE7 features, is because we need method handles which are introduced in Java SE7. So we look up the method handle for the, look up the method handle, and then we can pass that to the construct within. We can tell it which variable we're dealing with, which is endpoint 1, and we can reference back to the object that we're containing it within, which is this. So then the JVM can treat the object as if it were intrinsic, as if it were like a struct within a struct. Now, clearly, it's not going to do that, so as I'll explain in a moment. But what it can do is it can lay things out in memory such that dead reckoning can be used to calculate the address, because we know where those objects are relative to the supposedly enclosing object. Only thing that's also needs to be dealt with there is the idea of like if you do reflection-based overwrites, but that's kind of a bit of an edge case. So what we end up with is not actually putting the objects inside. So we don't take our points and put them inside the line. We still have the references that we need to follow to get to those objects. But what we do is we place the 2 point objects contiguous with our line object. If we want to reference endpoint 1 and endpoint 2, then yes, in the unintrinsified version, you simply follow the link from line 1, endpoint 1 to the point, endpoint 2 to the point, everything works. Once the JVM knows about that, it can do things to improve performance. So now it can say, oh, I know that I'm treating this as if it were one object. So I know that the point is immediately following the line object and the other point is immediately following that. So it can do dead reckoning to figure out where the values are. It doesn't have to follow those links. It knows they're immediately after the line object. Again, from the point of view of garbage collection, this will be treated as a single unit. It will be maintained as a contiguous area of memory and moved around as a single unit. In terms of the struct with an array at the end, what we have is the idea of subclassable arrays. So we create an array of primitive longs, primitive doubles, and so on. And there's also a reference array if you want to have an array of any kind of object. And what this allows us to do is then say, okay, we want to have a structured array which will actually have an array placed at the end. And so it will, again, put the array at the end and treat it as if it's one unit when it comes to moving things around in terms of garbage collection. The nice thing about this is everything is composable. So we can end up with some very kind of complex situations. Start off with our heap, where everything's going to go. We could create a structured array which contains objects which are themselves structured array of object foos. That will contain objects which are structured array of foo. But then if we look into foo, what we could find is that foo actually contains a couple of intrinsics. So this is the struct within struct. So now we've got a bar object and a baz object, which are being placed at the end of the foo object to treat them as a single unit. Those in turn are being put into a structured array, and the structured arrays of those are then being put inside a structured array. But then we could also have a structured array at the end of that of type mu, and we can give it an intrinsic length of 4. So we say, okay, there's a fixed length array at the end of that, and everything is composable. What that effectively means is that that really complex structure will be completely flat in memory. So it will be treated as a single object when we're doing garbage collection. It will enable us to, in a JVM which is optimized for this, to do striding. It will enable us to do dead reckoning, to find things and avoid a lot of unnecessary lookups through object references. From a status perspective, there is code out there already, so you can go to GitHub, objectlayout.org, follow the link from there. Gil says that he's still trying to work out the spelling of some of this, so some of the naming of the classes and so on might change a little bit. There's an intrinsified implementation for Zing, which is our JVM, our commercial JVM, and we're looking at how to implement it in the OpenJDK source code as well. We have done some experimentation, and we found that by using structured array underneath the hash map and looking at how get performs with that, because that's clearly doing reads from that and we can take advantage of the things that I've explained, we get about a 6% improvement in performance. So that's, that's not bad. It's something that could be very useful in certain situations. Next steps are obviously to take this code, which is external to the JDK, and try and bring it into the JDK. So that will require things like a JDK enhancement proposal. It will require inclusion in the JSRs that are created for whatever version of Java this might be included in. Certainly, it most likely be 10. It's not going to be 9 because we're too late for that, but maybe we get it in 10. Just to summarize, as I say, new classes, object layout, star. The idea is to move that into the Java namespace at some point. It will work out of the box on Java 7, 8, and 9, but for JVMs which know about these things, then it can optimize it. It can get better performance out of it. And that is pretty much it. So I think I've got a few minutes left, maybe 3.5 minutes left for Q&A. So if anybody's got any questions, I'm certainly happy to answer them, if I can see anybody. Ah, I see a question.
My question is, as you treat big objects or even arrays or whatever as a single chunk in the memory, do you have any effects of suddenly have to garbage collect huge amounts of memory as a single unit, like megabytes?
Well, it depends. If you're going to create a very large object, then depending on which garbage collection algorithm you're using, if you try and create a very large object, probably what's going to happen is that the JVM will be sensible enough to know that, let's say you create a structured array with, I don't know, like 10,000 elements in it, all of which have got fairly big-sized objects. The intrinsified JVM will look at that and go, oh, that's going to be a really big object because you have to create everything in one go. So rather than doing it in the new generation, it'll put it straight into the old generation. So if it puts it straight into the old generation, then it'll be contiguous in memory. Unless you do a full compacting garbage collection, it won't need to be moved. So it's only when you do, if you were using a garbage collection which needed to do a full compacting collection, then it would need to be moved. But if you were using Zing, for example, then you don't do a full compacting garbage collection, so it's not an issue. In an unintensified version, then you might find that it would depend on how the young generation was laid out and what kind of things were happening there. But yeah, I mean, it's at that point, it would really be no different to just creating a large number of individual objects. They would just get moved at some point when you did garbage collection. I don't think there'd be any significant impact. Does that answer your question?
Sorry, I might have missed something. I have a question. You said that objects in those structures reside in a specific slot, sort of, which allows this dead reckoning. but at the same time, they're also available for referencing from the outside code, from the outside world. So if I have a reference to one of those objects in my structure, and then I want to remove it from my structure, what happens then? Because I have outside pointers pointing to it, right? Outside references.
Yeah, well, you can't remove it. That's the point.
Ah, so it's static.
Yes. Yeah, it's immutable. The structured array is immutable. So you can't actually remove objects from the structured array. So that's the answer to that one. This is pretty simple.
So the lifetime of an element in the structured array can be longer than the lifetime of the structured array itself.
Absolutely, yes.
That means for things like Shenandoah, we would still need forward pointers for every structured array element.
Well, so the point is that they're not going. The objects in the structured array will not be any different to a normal object. So they will just be Java objects. It's just that the container is what's providing this this level of improvement in performance. So yes, the objects themselves could live longer than the structured array, and the structured array can be garbage collected. Any of the elements within that which aren't referenced can be garbage collected, but the objects that are still there are just like normal Java objects. So you can maintain a reference to it. You can use it. Does that? No. Good. I don't see anybody else handing their hand up, so I'm going to go with okay. Thank you very much.